here is another type of problem. It would take Sue 4 hours to paint a room alone. It would take Bob 5 hours to paint the same room alone. If they were to work together, how long would it take for them to paint the room together, complete the job together? All right, this is what we call a rate of work problem. Obviously, if Sue and Bob paint the room together, it's going to take them less time than any one of them working alone. So let's just try to sort out what's going on here. We have the time to paint the room by Sue and Bob, and then we're going to look at them doing it together. What do we know? What do we not know? All right, so I'm just trying to sort the information out. A chart is often a good way to do this, although not completely necessary. The time in hours, Sue, it takes her 4 hours to do the full job. It takes Bob 5 hours to do the full job. Together, well, we don't know. It's going to take them X hours together, knowing, like we said, that X is going to be less than 4 hours for sure. All right, now we really can't work with the times the way they are because each person is working at a different speed. So to try to equalize that different rate of work factor, we are going to look at the rate, and specifically the rate per hour. In other words, the fraction of the job done in 1 hour. So if we think just about 1 hour, if Sue can do the job in 4 hours, then in 1 hour she would do 1/4 of the job. That's the fraction of the job she would do in 1 hour. Bob would do 1/5 of the job in 1 hour, and together they would do 1/x of the job. Now what we have done by turning these into a rate is we've made these fractions here possible to add, because we know that the fraction of the job done in 1 hour by Sue and the fraction of the job done in 1 hour by Bob together should be the fraction of the job done together, which is 1/x of the job. All right, we have an equation to solve, so let's solve the equation. We can multiply both sides of our equation by the common denominator, which would be 20x. Distribute this through. This will be 5x plus 4x is, the x's cancel out on the right side, so we have 20. 9x is 20, so x is 20 over 9, which would be 2 2/9 of an hour, which is the time to do the job together. Therefore, if Sue and Bob work together, they can paint the room in 2 2/9 of an hour. Let's look at one more problem involving rate of work. Two things working together. So in this situation, we have a cold water tap, which if you turn it on by itself, it can fill a container 2 hours faster than if you just turned the hot water tap on alone. The two taps together, if you turn them both on fully, they can fill the container in 80 minutes. How long does it take each tap to fill the container on its own? All right, so again, our strategy is to first of all look at the time it takes for each component to work individually. So we have the cold tap, the hot tap, and we have the two taps together. And now I've got a difference here, but I've got hours happening here and minutes happening here. So I'm going to use a common conversion here. I'm going to use minutes, and because together the two taps can fill in 80 minutes, I'm going to put 80 here, time being in minutes. And we want to know how long it takes each tap on its own. So this is the part we don't know. We just know that the cold tap can fill a container 2 hours faster. So in other words, the time, since we're talking about time, of the cold tap versus the hot tap, if the hot tap is X minutes, then the cold tap is going to be 2 hours faster, which is 120 minutes less. All right, now to equalize these components, since they're working at a different rate, we have to look at the rate, or the percentage of the job, the rate of filling in 1 minute. So let's start with the together column, since we have a number there. If it takes 80 minutes for the two taps working together to fill the tank, in 1 minute, 1/80th of the tank will be filled. And so on the hot water tank, if it takes X minutes to just use the hot tank, the rate that's filled in 1 minute would be 1 over X. And for the cold, 1 over X minus 120. And because these are now equalized in terms of rate, or percentage filled, the amount filled, the proportion filled by the cold tap plus the proportion filled by the hot tap would equal the proportion filled by both taps together in 1 minute. And there's my equation. Let's solve the equation by multiplying both sides by the common denominator, which would be 80 times x minus 120. Distribute this through. On the first term, the x minus 120s cancel out. On the second term, the x's cancel out. And on the right side, the 80s cancel out. And we now have our equation without fractions. I'm going to set my equation to 0, x squared. I'm going to have 160 here, brought over to the other side would be minus 280x plus 9600. So we have an equation we need to solve, likely by factoring or quadratic formula, but I could also use my graphing method to do this, which might be helpful in this situation where we've got numbers that are particularly large. I'm just going to put in my corresponding function for this. And I know that this graph is a parabola. It's likely not going to show up here when I go to graph it, because I'm going to have to extend my x dimensions by quite a lot. Not really sure how much, but let's just see what that does. Okay, I see one number going one line there. Let's maybe make this 300 and see what happens. All right, and if I go to zoom fit, I can see the bottom of my problem. All right, so why did I do this? Because I know that the x-intercepts of this graph are the solutions to this equation. So if I solve graphically with my calculator, let's just grab this one solution right here. I don't know if this is a nice number or not. It actually is, it's 40. So coming back to my equation then, I know that if I had factored this, since 40 was an intercept, x minus 40 would have had to have been in here. And then I can work out what this would have to be. 40 times something is this. And I can see that that's 240 if I use a calculator, which is also my other x-intercept on my graph. Anyway, I get x is 40 and x is 240. Now if I look at how reasonable these answers are, keeping in mind that x represents the time to fill the tank just with the hot water tank, and I can see that this cannot be 40 if together it takes 80 minutes. This number is going to these numbers are definitely going to have to be larger than 80. So based on that, I know I can reject 40. It doesn't satisfy the parameters of this question, which means that x is 240 minutes. So therefore the hot water tap takes 240 minutes. The cold takes 2 hours less. That would be 120 minutes. In other words, the cold tap, working alone, can fill the container in 2 hours, and the hot would take 4 hours. And together, it would only take 80 minutes.